Hi everyone, this is Robô Brain, and we're here today to talk with you guys a little bit of our experience in the project and in competitions. I'm Felipe.
Hi, I am Alexandre.
Hi, I'm Matheus.
Hi, I'm Aloysio.
Sure. So we started in 2016, and in 2018 we were separated into two groups. Me and Matheus from Robô Brain, and Aloysio and Alexandre from Tríplice Intente. And in that year, Tríplice Intente won the ninth place and the Maker Award, and RoboBrain won in first place and the right to participate in RoboCUP 2019 in Sydney, where the team won the Best Hardware Solution Award. Then in 2019, we fused both teams to participate in the Nationals. For the hardware part, Aloysio can start explaining a little bit of it.
Sure. For programming, we use Arduino AT Mega, and for the part of the movement of the robot, we use two Dynamixel AX12A that are connected by one serial port. And for connect and amplify the number of pins and ports that Arduino has, we use manually made shield, or PCB, to connect everything, to connect our voltage regulators and the sensors and all the components that we use. Schematic. So we drew the schematic in the software EDA, like you see in my screen. And here we have all the components, all the links, all here we have everything that we used. So we drew step by step as our necessity. So we have like gyroscope pins, color sensors, the array that we use to track the line, and the voltage regulators. So here's 80 mega. Then we took this schematic and converted it into a PCB, and for have this physically, we used a manual process. We take laser printer and printed the schematic in a copper board. So then we used an acid to corrode and decay the circuits in the board. And then what we did is solder everything and start to use as we use it all the year.
About the body of the robot, it was created with 3D pieces that we've designed with software like FreeCAD, OpenSCAD, AutoCAD. It was better for us this way because it gave us a lot of freedom to produce customized pieces that fulfill our necessities just well. But all of this won't be anything without the main part of our work, the code, which can be explained better by Alexandre and Matheus.
So, this is our old code. We were still learning, so it's not the best it could be, but we organize our code by separating it files, each with its function. For example, the line track, in which we use a PID algorithm. And also we put all code dependencies in the libs folder, which in this case we have the motors and ultrasonic libraries. But one of the most special parts of our code is the library that we made. And this library was born as a side project because we needed a filter for infrared sensors. And after realizing that many other projects could take advantage of the library, we made it available on GitHub as an open source project. And you also can download it through the Arduino IDE's library manager. Oh, and also we have a documentation for this library, but we are still working with it. So you may have noticed that IDE is also different, and that's because we are using Visual Studio Code as a text editor because it has better code snippets, is very extensible, and has easy compatibility with Git. And this is particularly important for us as we use Git as a source control tool, which helps a lot in organizing the team's workflow. And Git is also being very important at this time due to the pandemic, as it allows us to work in an organized and efficient way in isolation.
So I'm going to talk about our algorithm for the evacuation zone. So this is our code for it. The functions that are not implemented here are in the is features. Is stands for evacuation zone. So the algorithm is quite simple. We just circle around the room looking for victims until there is little time left. To illustrate this, imagine we enter the room. We say that the last direction we turned is going to be the direction to the largest portion of the room. We can see this by the distance we read by the ultrasonic sensors on the sides. We have one on each side and two in the front. So when we arrive here, we say that the last direction is left, because when we encounter an obstacle or a wall, we're going to try to go to the opposite direction we previously turned. So we can see that is something here with the ultrasonic sensors, and with we can differentiate it between an obstacle and victim and a wall with the two on the front. So this is the victim, we catch it, we continue the algorithm, we arrive at this, we catch it. So you can also differentiate between living and dead victim, so you can save the living one first. So we deposit these two here, catch this, continue. Then we arrive at the obstacle. You can see that it's an obstacle, not a victim. So we go to this direction because it's the only one. And here we go to the right because we turned to the left previously. So we arrived at the start. But we always track the position of our robot, so we can see that we are on the start because we save the position of the start and the triangle. So we're going to turn to this direction, then this, and rip in this, and eventually all the victims will be here, or almost all of them. And see, we have little time left. In that case, if we have victims, we just go and deposit them, and then leave the room for extra points. So the thing is that we don't have an encoder, so we had to track the position based on the time the robot travel in direction. Some basic trigonometry does that, but it's not that accurate. So we try to say that the velocity over time function would be a quadratic, and the time it traveled will be the linear equivalent of that velocity we plug in. So we will say that the integral of that quadratic between the roots will be equal to the distance we want to travel, and then we find a formula for the coefficients and plug in the code. So it doesn't just accelerate abruptly and deaccelerate abruptly. So it came out nice, but it wasn't perfect, and because of that we still had some other issues, some other major issues with the evacuation zone for debris, for example, which Alois is gonna cover for us.
Okay, now I'm showing the evacuation zone algorithms in practice, in time-lapse due to the time. However, we had successful results when we were testing, as well as you can see. In the day of the competition, we didn't succeed well. We weren't expecting this amount of toothpicks, therefore our algorithms could not be able to precisely localize the robot. It means the robot could not smartly or generically map the room. So, because of this fact, he couldn't proceed and complete the execution of the theory of the algorithms.